Okay, we have already discussed, we have agreed that using test signals, we should be able to assess a performance of dynamic systems. But the question now, how are we going to assess it? How are we going to analyze the response of dynamic system to assess its performance? Now, let's consider a system with a transfer function of GS. And then to the system, we give an input of U, and the system will respond it by an output of Y. Based on the dynamic principle, of course, the Laplace of the output Ys will be equal to the transfer function Gs times the input in Laplace domain. So the capital Y is the Laplace of the Yt, the capital U is the Laplace of Ut. Model of a dynamic system, as we have already discussed before, can be represented in a differential equation. If you still remember, if you refer to engineering math that you have learned before, when you solve a differential equation, we always get two solutions, homogeneous solution and particular solution. Same thing to our dynamic system here. If you analyze it mathematically, you will have two solutions, homogeneous and particular solution. Or sometimes we call homogeneous solution as a natural response and particular solution as a forced response. But these are the two types of response from mathematical perspective. We are not really interested in mathematical things. We are an engineer here. So we will see a response of a dynamic system from engineering perspective. Let's take a look here again, a case of a dynamic system. You have seen this plot before. A dynamic system, to this dynamic system, you give a constant input yt indicated in red there, and then to the system will give an output of xt in dash green line there. As what we have discussed before, if you have a dynamic system, you give a constant input, the response will vary in time. Even though after some times, the response, the output xt will follow the input yt. Now let's take a look in more detail on the output xt now. As I mentioned, at the beginning, the output will vary in time. And then after certain time, the output will follow the input yt. So from here, from engineering perspective, I can differentiate an output of a dynamic system into two parts. The first part, at the beginning, we call it as a transient part, where the response is still varying in time. And the next part, we call it as a steady state part, where the response start to follow the input precisely. So again, from engineering perspective, the response of a dynamic system or the solution of a differential equation, we can classify it into transient response and steady state response. Same thing like in a case where on the dynamic system we give a sinusoidal input, the red one, yt. The response will be the dash green line, xt. Let's take a look in more detail to the response now. At the beginning, the output is still varying in time. It doesn't really follow the input. That is a part where we call the output as a transient response. And then after sometimes the output can follow the input, we call the later part as the steady state response. Okay. Where is the border between these two responses? We cannot really draw a clear border there. But what I can say, the transient part is when the response is still varying in time. The steady state part is when the response, the output can follow the behavior of the input. What is the correlation between transient and steady state to the natural and forced responses, or to the homogeneous and particular solution. If we are going to draw the line between these two things, the transient response is more dominated by the natural response or by the homogeneous solution, while the steady state response is more dominated by the particular solution. But these two are not the same thing, so it doesn't mean that transient is the homogeneous solution and steady state is the particular solution. No, it doesn't mean that. But all I can say that transient is dominated by the homogeneous and steady state is dominated by particular solution. So when we are going to assess the performance of a dynamic system, we normally assess it with two numbers. The first one is accuracy and the second one is speed. To assess the accuracy, you refer to the steady state part from the response from the output, while the speed you can assess it from the transient part. I will give an illustration about what is accuracy and what is speed in the next slide. In short, I can say that speed will tell you how fast the system will follow the input. How long does it take for the system to make the output follow the input? That is how we tell by using the speed. In this topic, we mainly will discuss on the steady state response and how to assess the accuracy. The transient response will be discussed in the subsequent topics. Okay, now let's take a look in more detail on the steady state response. Steady state response is the later part of the output. This means we are looking at the response in the future time when time approaches infinity. This will ring a bell to us. We can evaluate the steady state response using a final value theorem. We have already discussed about this final value theorem in the first week. So if you have a system again with a transfer function of gs and you give an input to the system of u, the system will give an output of y. To evaluate the final value of the output or to evaluate the steady state value of the output y, you can apply the final value theorem. The final value of y, or I can say it as the value of y when time approaches infinity, will be equal to limit s to 0 of s times the Laplace of the ys. We have already discussed about these things about the final value theorem. But from the system, you know that ys is equal to gs times us, right? So you can evaluate the steady state response by using this expression limit s to 0 of s times g times u. Before we continue, let me introduce you with one new terminology. This is called a DC gain. So what is a DC gain? By definition, DC gain is the steady state response or the final value of the output when you give a unit step input to the system. Still remember what unit step input? Unit step input is a constant input where the constant is equal to 1, as you can see in this right hand side of this slide. Okay, so based on the final value theorem that we discussed in the previous slide, we can find the DC gain. The DC gain is the final value of the response yt when we give an input of unit step. So the final value of the output is equal to the limit s to 0 of s times y. But now you know that y is the unit step response where the input us is equal to 1 over s in Laplace domain. That is the Laplace of unit step signal. So from here, you know that ys is equal to 1 over s times gs. You can just apply this to the final value theorem. Therefore, the DC gain will be equal to, again, limit s to 0 of s times the output ys. But now in this case, you know the output ys is equal to 1 over s times gs. And this s will cancel the s from the step signal. So then, technically, from mathematical point of view, DC gain is equal to limit s to 0 of the transfer function gs. So if you want to evaluate DC gain, you just substitute 0 to all of the s's in your gs. Let's take an example of this system. So I have a system where the transfer function is expressed as you can see in this slide. 3 times s plus 2 divided by s squared plus 2s plus 10. DC gain of this system, you can find it easily. You just substitute all of the s's in your gs by 0, and then you will get the DC gain. So the DC gain will be equal to 0 0.6. Again, what is the meaning of this DC gain? So this means if you give a unit step input to this system, the system with the transfer function of gs, the final value of the output will be equal to 0 0.6. This is the final value when you give a unit step input. If the input that you give to the system is 5 times the unit step, which means you have a step input, but the value of the constant is not 1, but instead you have 5 in here. So this is what it means by 5 times of unit step, 5 UT. If you give a step input with a value of 5, then of course the final value of the output will be just simply 5 times the DC gain. 5 times 0 0.6 is equal to 3. Okay, we have already discussed what DC gain is, and we have already discussed what is the steady state response, how to evaluate the steady state response. Now let's take a specific case on a closed loop system, on a controlled system. As an example, you can consider this as the air conditioning system, the one that we discussed in the very first week of this course, where G1S here represent the transfer function of the heat pump together with the controller, and CS represent the temperature of your room. US is the temperature that you set in your air conditioning remote controller. So the logic of the controller will say if C, the output, is greater than U, the controller will ask the heat pump to start. But when C is smaller than U, the controller will stop the heat pump. That's how the air conditioning system works, right? We have discussed that in the very first week. Now, how do we assess the performance of this air conditioning system? Or in general, then how do we assess the performance of this closed loop system? Basically, we assess it by looking at the value of E. E is the output of the summing point. If you have a good air conditioning system, after you turn it on and after you set the desired temperature in your remote controller, if you have good air conditioning system, after sometimes when the steady state condition is reached, the temperature of your room, which is C, should be equal to the temperature that you set in your remote controller, which is U. Which means if you have a good air conditioning system, after sometimes, after the steady state condition is reached, C should be equal to U. If C is equal to U, then your E will be equal to 0. That condition, E equal to 0, will be reached when the steady state condition is achieved. So, by looking at the steady state value of E of the error, we should be able to assess the performance of the system in terms of the accuracy. If the steady state value of E is equal to 0, that means you have an accurate closed loop system. That means you have an accurate air conditioning system. Okay, now let's try to evaluate the accuracy of a closed loop system, or you can consider it as an air conditioning system, when you know the transfer function of the heat pump together with the controller. The transfer function of the heat pump and the controller is represented by G1. You still remember, right? The controller together with the heat pump is on the forward part. So G1 is the transfer function of the heat pump together with the controller, or from the technical perspective, we call G1 as the forward loop transfer function, right? Now let's consider we have a unity feedback system where the open loop transfer function or the forward loop transfer function is equal to G1. We are going to assess the accuracy of the system by looking at the steady state of the error, steady state of the E value. We know that based on the summing point there, we know that E is equal to U minus C, right? But then at the same times, if you look at the forward part there, C is the output of G1 and E behaves as an input to G1. So from there, we can also conclude that C is equal to G1 times E. Therefore, I can express E. I can substitute the second equation here to the first equation. E will be equal to U minus G1 times E. Or after I do some mathematical manipulation, E is equal to this equation, U divided by 1 plus G1. Now we are going to assess the accuracy of this system. How to do that? We just simply use the final value theorem, the one that we just discussed in the previous slide. Now, you can also evaluate the accuracy of the closed loop system by using the closed loop transfer function. This is another alternative to the approach that we used in the previous slide. Let's take a look on the same system, a unity feedback system with a forward loop transfer function equal to G1. In this case, the closed loop transfer function of the system will be equal to G1 divided by 1 plus G1, right? You know how to do this. The closed loop transfer function will be equal to the forward loop transfer function divided by 1 plus open loop transfer function. So G here is the transfer function of this closed loop system. So I can redraw the closed loop block diagram into something like this to simplify it. So again, then G here is the transfer function of this closed loop system. While G1 is the transfer function of the forward loop system for the forward loop part of this closed loop system. Same thing then here. I want to express the E, the error, in terms of G. As E, as we discussed before, is equal to U minus C, and at the same time, if you look at the closed loop system, this one, we know that C is equal to G times U. So I can also again express E in terms of G. So I just simply substitute G times U to the C in the first equation, and then I can express E as follows. So now I have two alternatives to express the E value. I can express it in terms of G1. I can also express it in terms of G, the closed loop transfer function. So once we know E, we can assess the accuracy of the closed loop system. How to do that? Same like what we discussed before. If you want to assess the accuracy of a closed loop system, you just have to find the steady state value of the E, steady state value of the error, or the final value of the error. How to do that? Of course, you can just simply use the final value theorem. So the final value of the error E will be equal to limit s to 0 of s times E. You can use either of the two equation to express the E. You can use the value of E with respect to G1. You can also use the value of E that is expressed in terms of G, where again G1 is the open loop transfer function and G is the closed loop transfer function. Depending on what the input is, you can evaluate the accuracy of the closed loop system from the steady state value of the error. So if you know the input U, you can find the steady state of the error. Let's now take a case when the input is equal to unit step signal. So in this case then, the value of U as the input, because we have a unit step input, the value of US will be equal to 1 over S. So you can evaluate the steady state error by using the two equation that I showed in the previous slide, where the steady state error can be calculated based on G1 or based on G. But of course, in this case now, our input is equal to 1 over S, because the input is a unit step signal, and unit step in Laplace domain is equal to 1 over S. So using this expression, you can find the steady state value when the input is unit step. Let's take another example here. We take a look on this particular system. So we have a closed loop system again here. We have G1 as the open loop transfer function here, and G1 is known. G1 is equal to 3s plus 2 divided by s squared plus 2s plus 10. From here, we can just simply calculate the steady state error when we have a unit step input. If you know, if you have unit step input in Laplace domain, of course, unit step input is equal to 1 over S. Based on the equation in the previous slide, you can evaluate the steady state because of unit step input. This will be equal to 1 over 1 plus G1 S when S is equal 0. If you do this, you can find the steady state value because of unit step input. But the question that I pose in this example is, we are going to evaluate the steady state error when 5 times step input is given to the system. So the input now that is given to the system is 5 times unit step. So how to do that? Of course, you just simply have to multiply the steady state error when we give a unit step input by 5, because the input now is 5 times of a unit step. Okay, so you can try it by yourself to evaluate this equation, and then you will get that the steady state error, if we give a 5 times unit step, the steady state error will be equal to 50 over 16.